I'm Ross Bagurtis, and in this video, we'll be discussing the OSI model and encapsulation. In a previous video about network models, I talked about how the OSI model is used and organizes protocols into the different layers. Now, what we're going to find out is that as data moves off of our computer and onto the data network, it goes through a very specific process called encapsulation. And what encapsulation is we take a large chunk of data, we break it up into smaller pieces, and then we put those smaller pieces in virtual envelopes. And the process of taking that smaller chunk of data and putting it into an envelope, a virtual envelope, and then adding addressing information onto it, that process is called encapsulation. Let's take a look at how it works. So we start at the application layer, layer 7. So if we use an example where we're talking to a website and we want to retrieve data from a website, if we browse to google.com, google.com will then send its web page back to us. And the web page that Google sends to us is really nothing more than a file. It's a bunch of data. It's kind of like a Word document, if you think of it like that, or an Excel spreadsheet. We just use a different application, in this case a web server running HTTP, and we format our document in an HTML format, hypertext markup language, and then Google will send us that file, and that file will be displayed on our web browser. Now, before Google can send that data is going to be in a large chunk of information, and it's going to be sitting at the application layer. And HTTP, remember, operates at the application layer. So as Google begins to send this, it's going to collect the data, the file that it wants to send to our workstation. And then the application layer will begin to send that data down to the transport layer. So what I have drawn right here is this blue box will be the large chunk of data. This will be Google's website that it's sending to our workstation. And it's going to break it up into these smaller pieces then. Those smaller pieces that it breaks it up into are then encapsulated inside of the transport layer header or the transport layer virtual envelope. And so we put the first data segment inside of that envelope, and then we put header information on it. And the transport layer header is going to have a source port number, a destination port number for its addressing, and then other information is going to be included in the transport layer header. Now that other information is going to be very protocol specific. If we're using TCP, the other information in the header is going to contain window sizes, acknowledgement numbers, as well as other pieces of TCP in order to make transport layer operate properly when using the TCP protocol. If we're using the UDP protocol, which is the other protocol that operates at the transport layer, we're going to see other information in that other info field in the transport layer header. Now the source port and the destination port here are going to identify the session between the two endpoints. And we're going to take a look at this in more detail in a future video when we look exclusively at how TCP and UDP operate. But the source port and the destination port number are truly there to identify a session between the two endpoints so that we know that we're operating from our web browser going to a web server. And that will have a very specific identification of a source port and destination port number. Once the transport layer header is added onto our data, we call this chunk of data now, we call this a segment. So all transport layer data is encapsulated in something called a segment. Once the segment is created, we then hand that information down to the network layer. So then we take the transport layer segment, and that becomes the data portion of our network layer envelope. And that network layer envelope is called a packet. And inside of the packet, we put in a source IP address, a destination IP address, as well as some other information to make Internet Protocol work. So the packet then becomes the segment plus network layer header information. So we're kind of nesting these envelopes. If you think about it, this is kind of like sending a letter to your friend, except we're doing it in a very interesting way. We're going to take our letter at the application layer, we're going to fold it up, and we're going to put that into an envelope at the transport layer. And then the transport layer envelope, we're going to stick into another envelope, and that envelope is called the packet. And we're going to label that envelope now with the source IP address and destination IP address. And the idea of that is just like we would use the US mail. We're using the source IP address as my return address. The destination IP address is the web server or other networked device that we're communicating with. Once we have this packet created, we then send it down to the data link layer for processing. And the data link layer is going to take the packet at the network layer, and it's going to put it yet in another envelope. And it's going to put it in an envelope when it's going to add a data link layer header. And the data link layer header plus the packet now becomes this new envelope, this new virtual envelope called a frame. So the frame is going to have the destination MAC address, the source MAC address, as well as other information that's related to the layer 2 network that we're using to communicate. Once the frame has been created, it then sends it down to the physical layer. The physical layer converts the frame into pulses of electricity or light or photons or waves or whatever you want to call it, and that's basically interpreted as ones and zeros being transferred over the physical layer medium, whether that be a copper wire, a piece of glass, or wireless communication. It's all going to be transferred in the ones and zeros to get it from one endpoint to the other endpoint. When the other device receives the ones and zeros, it will reassemble it into the frame. It'll examine the frame and make a decision of what to do with it. If the frame is destined for the device that received it, it will then extract the packet from the frame, examine the packet. If the packet is destined for the device that received it, it will then extract the segment out of the packet. The segment will then be interpreted and sent to the proper process in the receiving device to be processed further at the application layer. So we see this encapsulation and de-encapsulation process happen as we send data from one device on our network to the other device on our network. This encapsulation process is really the core of data networking, and it's really important that we understand this because over time we are going to have to troubleshoot issues at different layers of the OSI model. If it's a data link layer issue, it's going to be related to the network interface cards and switches. If it's a network layer issue, it's going to be related to IP addressing and routers. If it's a transport layer issue, it's going to be related to port numbers and firewalls. And if it's an application layer problem, there may be something wrong with the service on the server that we're using. So we can later use our encapsulation process to better understand how the data network operates and use it to troubleshoot. If we take a look again then at the protocols that operate at each layer of the OSI model, we can then start to assemble our knowledge of the basic protocols that the internet operates on and how they interact with each other. I've come up with this chart that describes how the main protocols that we use at the application layer interact with the rest of the OSI model. So up at the top layer here we have the application layer, and we have HTTP, HTTPS for web, Telnet and SSH for remote access, FTP, SFTP for file transfer, and you'll notice TFTP actually is way on the end here, and I'll explain that in a moment. We have IMAP, POP3, SMTP for email, and DNS for domain name service, and you'll notice that DNS actually fits in two categories here as well. At the transport layer then, you'll notice that at the transport layer what I've done is I have listed the port number for these well-known application layer protocols right below it. And notice that I put them though at the transport layer of the OSI model. So HTTP always operates on port 80, HTTPS 443, Telnet 23, SSH is port 22, FTP actually uses two ports, 20 and 21. SFTP, Secure FTP, uses port 22. And if you notice, that's the same port number as SSH. And the reason for that is that we actually use FTP as the core process in SFTP. We just encapsulate it inside of an SSH session. So we're going to use the encryption services of SSH to encapsulate our FTP session, and we call that service SFTP. IMAP is port 143, POP3 operates on port 110, SMTP operates on port 25, and DNS operates on port 53. TFTP, this is always my favorite. I was a big Bill and Ted's Excellent Adventure fan back in the day, whenever that came out in the 80s and early 90s. And I always remember TFTP because it's port 69, dude. So if we take a look then at how I have my chart set up, you'll notice there's this large blue box here that's associated with TCP, and then this smaller gray box that's associated with UDP. If we take a look at each of these, HTTP, HTTPS, Telnet, and so on, all of these protocols make exclusive use of TCP at the transport layer. So the protocols I have listed here all use TCP at the transport layer. As a matter of fact, most application layer protocols in today's networks use TCP at the transport layer. However, there are two protocols here, DNS and TFTP, that actually use UDP at the transport layer. Well, first let's take a look at TFTP. TFTP was written to be a very lightweight protocol. And because it's a very lightweight protocol, it doesn't want to use all the extra overhead that's involved with using TCP. So instead, we're going to use UDP when we use TFTP. Same thing with DNS. Now, DNS falls in two categories here. Sometimes DNS needs to use TCP for reliable communication. Sometimes DNS is going to use UDP because it doesn't want all of that TCP overhead. Now, in a future video, we're going to discuss TCP and UDP in great detail because it's very fundamental to understanding how the data network works. And when we do that, I'll explain why we use DNS with TCP and DNS with UDP. So the big point I'm trying to make here, though, is that these application layer protocols are designed to work specifically with a transport layer protocol. If we notice now, all of the protocols at the application layer and transport layer, whether it be TCP or UDP, all of those protocols are going to make use of Internet Protocol at the network layer. So the network layer becomes this unifying body to encapsulate any application layer traffic, any transport layer traffic into a unified packet that can be transferred across the network. So this way we can have devices that all speak the same language at the network layer in order to move the packet from one side of the network to the other side of the network. Now, in order to move that packet from one side of a network to the other side of the network, especially if we're using the internet, we're traversing a very large distance through quite a few different organizations to reach our endpoint, we may see many different types of data link layer protocols being used. So if we're using a physical wire to transmit the data, we may be using Ethernet, serial communications, or some other type of communication at the data link layer. If we're using fiber optics, we once again can use Ethernet. We can also use asynchronous transfer mode, or ATM. And there are other fiber optic technologies out there that we can use to transmit data at the data link layer over fiber optic. Last, we can use wireless. And in the wireless world, we have the 802.11 Ethernet wireless specifications. And there's other wireless specifications out there as well as some proprietary ones. So even though we're encapsulating with IP at the network layer, we can take that packet then and we can move it across any type of network we want. So in order to understand what's happening here, how we're taking IP and moving it over different technologies here, let's take a look at our home network again. So here's a very basic drawing of a home network. We have a wireless laptop, a wired computer hooked up to a wireless router. That wireless router is connected to a cable or DSL modem, which is then hooked up to the internet. So if we assume that you're using a cable modem at home, what would happen here is if you wanted to get Google's website and you're on your laptop, you would type in www.google.com into your browser and hit enter. That would then trigger your computer to set up the application layer information for the request. It will then send it down to the transport layer to get formatted into a segment. It'll then send it down to the network layer to get formatted into the packet. The packet then will get encapsulated with wireless Ethernet here to communicate with the wireless router. So my laptop here will then put my IP packet inside of a wireless Ethernet frame and then send the frame at the physical layer over to the router. The wireless router then will extract the IP packet from the frame. It will then build a new frame using Ethernet to send that frame from the wireless router to the cable modem. Except this time, instead of using wireless Ethernet like we did from the laptop to the router, now we're going to put it in a different frame for wired Ethernet, which will then send it from the router to the cable modem. The cable modem will then take the packet out of the wired Ethernet frame. It will then put it into a new frame, which is called a DOCSIS frame, DOCSYS. And that DOCSIS frame then can be sent from the cable modem out to the internet, to your internet service provider. Once it's at your internet service provider, this process of removing the packet and re-encapsulating it into a new frame dependent upon the layer 2 technology used to connect the devices together will continue to happen again and again and again. This is much like a shampoo bottle, right? Rinse, wash, repeat. And we're going to see this a lot in data networking, where everything we do is a repetition of a process that we've seen again and again and again. And a bit of advice here about that, and I'll try to remind you about this as often as possible. Repetition is key to learning data networking. The more often you do it, the more often you see it, the more often you touch it, the better understanding you will eventually have. And this is really important because I want you to understand exactly how a data network works. And the best mechanism to do that is practice, 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 practice. You can't possibly get enough practice when working with data networking. The more practice you have, the easier things come together. So let's wrap up this encapsulation process and the OSI model. And we're going to be using the OSI model now for the rest of the CCNA curriculum because everything we do in data networking falls into one of these 5 layers of the OSI model. So up at the application layer, here again are the protocols that run on the servers, HTTP, HTTPS, FTP, and so on. So at the transport layer, here's where we use port numbers to address our data, and those port numbers are used to identify a communication session between 2 endpoints. Remember I said earlier, the transport layer has similar functionality built into it in the same way that we use our telephone. We pick up the telephone, we listen for the dial tone, we dial a phone number, we wait for it to ring, we wait for our friend to answer, and then we can begin our conversation. The transport layer uses port numbers much in the same way that we use the telephone number to set up a session between 2 telephones when making a phone call. At the transport layer, we call our datagram a segment. Now, I haven't really used the term datagram before, so let me talk about that. Datagram is a generic term to refer to an encapsulated piece of data. So any encapsulated piece of data I can refer to as a datagram. So the datagram at transport layer is called a segment. We go down to the network layer. Here we're using IP addressing to address our packets. So our datagram at the network layer is called packet. Once we get down to layer 2, we're going to use MAC addresses, especially if you're using Ethernet. And we're going to call the datagram there a frame. And then down at the physical layer, this is either going to be wire, fiber, or wireless. Now, something that's interesting to note about this, you're going to have to memorize and know with certainty that a segment is a transport layer function, a packet is a network layer function, and a frame is a data link layer function. When you're reading about and talking about data networks, many engineers, many books will get loose with their terminology here and end up calling every kind of datagram a packet, whether they're referring to a frame, a packet, or a segment. This is especially true if you use a protocol analyzer like Wireshark, which is a freely available tool that you can download. And I highly recommend downloading and playing with Wireshark as you move through your CCNA training when possible. In Wireshark, though, most often the language they use to refer to datagrams is called packets. So we just have to use caution. You have to use caution here when we're discussing different types of datagrams inside of a network because they can have very different meanings. Traditionally, packet means the thing that has the IP addresses in it. Segment means the thing that has the port numbers in it. And frame means the thing that has the MAC addresses in it. So this wraps up our conversation about the OSI model, the encapsulation process, as well as how we address and label different datagrams at different layers of the OSI model. Thank you very much for watching, and I look forward to seeing you in future videos.